All right, so on this Verilog, let me show you one cool thing we can do with this. So this is a circuit we've seen before. So it's a module called glitch, that's a hint. It has an input A and an output X. So here's A and X. I'm just going to sketch along. And I'm using a pair of assign statements. I'm setting A bar equal to the complement of A, and then I'm setting X equal to the AND of A with A bar. So A goes through an inverter and creates a signal called ABAR, and then that gets ANDed with A, and that's our output X. And that's an inverter. So A bar, X. So 0 and 1 is 0, 1 and 0 is 0. So the output should always be 0, right? Okay, so one thing you can do in Verilog is you can put inside the assign statement a time delay. So I'm saying assign after 5 nanoseconds A bar equal to not A. And assign after 2 nanoseconds X equals A and A bar. So this has a propagation delay of 5 nanoseconds. This has a propagation delay of 2 nanoseconds. So tau sub p is just propagation delay. And when we worked through this on paper by hand, we saw that this could introduce a glitch, where this might become a 1, but it takes a while for A bar to become a 0, and so for a brief instant in time, we have a 1 and a 1 going into an AND gate, and the output can actually go high. So we can model that with Verilog by just putting these time delays on our assign statements. And now we run this thing from a test bench, which basically says set A to 0, wait 20 nanoseconds, set A to 1, wait 20, set A to 0. And if we do this, we can compile. We can, let's use test glitch. We can simulate it, and then we can look at the output waveform. So we can look at A and A bar and X, and let's zoom out. And here's what we're actually seeing. So A starts off at 0, goes up to 1, it comes back down to 0. A bar is the complement, but you can see the propagation delay here from 20 to 25. A bar is still a 1. And so during this period of time, you have a pair of 1s going into our AND gate. 2 nanoseconds later, the AND gate outputs a 1. This is the glitch right here. Right? Even though by our truth table X should always be 0, it pops up to a 1 for a brief period of time, for about 5 nanoseconds. And that's a classic glitch. Now if we had this output X feeding into something else that could respond to that 1, right, we could see where the effect of that glitch carries forward. And you know, sometimes glitches are harmless, sometimes they're catastrophic. Right? Sometimes this is why your rocket explodes on the launch pad. Just little timing glitches. So Verilog can help us with that, and as I've said before, most of these tools will do fairly sophisticated timing analysis. They'll do estimates for how much time it takes an input to propagate to an output, and you can say, what's the worst case propagation delay? And you can use that to help set your clock speed. So the tools get very sophisticated. All right, let's see what we got here. So we already played with this last time with the Xilinx tools, but this was the 2-bit adder example, right? So input 1 and input 2 are 2-bit values. Out is a 3-bit value. Let's well, we don't have to play with that more. So that constructs a 2-bit adder, right? Just by using the plus sign. And this goes through, does it hit all the possible combinations? No, but it hits most of the interesting combinations of inputs and outputs. Oh, that didn't work. That didn't work either. So I don't know why I'm assigning out equal, assigning x to in 1 plus in 2, but anyway, out's our output. So let's set out equal to that. Alright, so there's output from there, so 2 plus 3 is equal to 5, 2 plus 2 is 4. Life is good. Alright, so here it's displaying the output values in binary, so 1, 0 plus 0, 1 is equal to 1, 1, for example, right here. But we can also expand these and go crazy looking at waveforms. But there's the way your timing diagram would look for a 2-bit adder. So if you haven't noticed, right, Icarus Verilog is a whole lot faster than the Xilinx tools, right? It's not as powerful. It's not doing all of the actual synthesis of figuring out how to put this onto a piece of hardware. It's not doing the detailed timing analysis and so on. But it's really, really fast, right? Which, like I say, if your goal is to spend your afternoon designing Verilog as opposed to playing with software, right, this is pretty much unbeatable. Especially if you have an environment you're comfortable with, right? So I'm doing this in Linux, right? So if you take 224, you learn all kinds of things that can help you with Linux, like command line recall, right? Or you know, !G will rerun the last command I type. It started with a G, which was GTK wave, so I don't have to arrow up. Or you can make shortcuts and so on and so forth. So that's a whole nother soapbox for another quarter. But make your work environment something that works for you instead of against you. So let's make a flip-flop. So toggle flip-flop. We normally think of it as having one input, T, but it's also got a clock. And it's got an output Q. Maybe it's got a Q bar output also. But probably 2 inputs, 1 output. So here's my T, which is an input. Here's my clock. Here's my Q. Okay, so wires versus registers. Okay, think of a wire as saying I want this variable to be able to connect something to something. Okay, it's really just something that can be assigned a value, and that value can be assigned somewhere else or used in an if statement or something. A reg is something that you want to have actually remember a value. Okay, at some point in time I want to be able to say set this variable equal to 7, right? If you're going to do that, that variable's got to be a reg. If you say I want this variable to have whatever value is coming out of this circuit, that can be a wire. It could also be a reg. But it really just needs to be a wire because we're going to take the output of this circuit and connect it to this variable, right? So it's really just the end of a wire. But if we say, you know, when the owl hoots 3 times, I want to take the output of the circuit and store that in this variable x, right? That's going to happen at one moment in time. And so that's got to be able to remember the value that you set it to. That's going to have to be a reg. So usually a reg is going to be a flip-flop, and a wire is just going to be something like a wire. Now, since we're inside a test bench here, we're doing things like saying, I want to set t equal to 0 at 2 nanoseconds, right? And then 45 seconds later, nanoseconds later, I want to set t equal to 1. Well, in between here, we don't want t to be undefined. We want t to continue to be 0 until 45 nanoseconds later, where we want t to be a 1, and we want it to remember that value 1 until 80 nanoseconds later when we set it to a 0. So t's got to be a register. Okay, so the clock, here's something that we can do. We can make a block that says always begin. This is what we call not synthesizable. If you were actually building this circuit on an FPGA, this doesn't do anything. But in a simulation, this has meaning. This says always, always, always do the following. We're not waiting for a positive edge of something or a variable change value. We're saying always do this. What is it that we want to do? We want to wait 10 nanoseconds and then set clock equal to the opposite of clock. So this is how we simulate an actual clock, how we get a signal to go up and down every 10 nanoseconds in this case. So it's this always begin block. And it's just kind of a trick we can use in Verilog when we're simulating to say, okay, I want the clock to toggle every 10 nanoseconds. So I got the clock toggling, I've got t as a register, and here's the actual code that makes a t flip-flop. So it says, at the positive edge of the clock, if t is equal to 1, set q equal to its opposite value. Well, that's exactly what a t flip-flop does, right? Positive edge trigger t flip-flop says whenever the clock changes from 0 to 1, check the t input. If it's 0, don't do anything. But if it's a 1, take the current value of q and toggle it. And that's what this statement, q is assigned not q, does. Okay, and remember, for the next few minutes, this really means just an arrow. It's not a less than or equal to. It's a funny ASCII way of drawing an arrow. So this q arrow tilde q means q is assigned the value not q. So there's the whole definition of a t flip-flop. If t is 1, when the clock ticks, toggle q. Otherwise, don't do anything. Yeah?
So you're using a register there in the homework. They're building a JK flip-flop and they use wires.
Yeah, so you could do this, well, there's got to be a register somewhere, though, that's probably being assigned to the wire.
There's a register for the output.
Yeah. So I could call this something other than q, and I could make q a wire, and I could assign q equal to, that internal thing. But ultimately, something's got to be able to remember in between these clock ticks. All right, so that's the module setup. This is the actual thing that makes the t flip-flop a t flip-flop. This is what drives the clock, and then the rest of this is just setting up the inputs. Yes?
Is wire quicker than register, or why would you not just use register if it works for both cases?
Because if I say assign register equals, it's not going to like that.
Okay.
right? So registers, you can use that less than equal assignment, but you can't actually use the assign statement. All right, so we set up test for VCD and say dump the variables. We start off with the clock is 0, Q is 0, and T is 0. That's just a one-time initialization. And remember, the clock's going to be toggling every 10 nanoseconds. So 45 nanoseconds later, we set T equal to 1, and then we set it to 0, and so on. So let's compile this. Let's simulate it. And then let's look at the waveforms. So we've got our clock. And let's look at the clock first. The clock's doing exactly what we want. It's clocking. It's going up and down every 10 nanoseconds. So that's kind of cool by itself. Let's look at our T input. So T is mostly low. Up here it went high for 80 nanoseconds and then it went low. And let's see what Q does. Well, it starts off low. Once the T input is high, the next rising edge of the clock, Q toggled. And it stayed a 1 until this next rising edge of the clock, and it toggled again and went low. And at the next rising edge of the clock, it toggled again and went high. And at the next rising edge of the clock, it toggled again and went low. But at the next rising edge of the clock, it stayed low because at this point our T input was a 0 again. So when T is 1, it's toggling every time the clock ticks up. When T is 0, it just stays where it is. That's exactly what a T flip-flop should do. So let's talk about synthesis. And remember my day one mantra about Verilog, the most important thing that I said you should know about Verilog? It's not coding. It's not a programming language. It's not describing an algorithm. It's describing a piece of hardware. Okay, so let's look at what hardware is described by Verilog. Assign x equals a and b or not c. That's actually going to take an AND gate. It's going to connect the two inputs to a and b. It's going to take c, run it through an inverter, and it's going to OR that with the output of the AND gate. And it's going to connect the output to x. So this is saying, build me this piece of circuit, connect a, b, c, and x thusly.
So if we like put that in a like an always begin block, would it always be checking if x meets that criteria?
Yeah, so we're going to do always in a moment. So as soon as we say always, we've probably got flip-flops in the picture. All right, so let's do always at positive edge clock. And we can't really do an assign statement inside an always block. Because remember, assign is saying build this, connect its output to this. And if we put an assign statement inside an always block, we're saying whenever the clock ticks, I want you to build a circuit. I want you to connect this to this with a wire. And the way Verilog is written, it doesn't let you actually like modify the circuit while things are running, right? It's describing a static picture of a circuit, right? I'm working on changing that. That's another story. So, so we can't use an assign statement, but we can do something like this. You know, if t equals 1, X is assigned to not X. So something like RT flip-flop. Yeah.
So we actually tried doing some Verilog earlier today, and do we always have to include a begin, like after every if statement? And if not, when do we do that?
I think I always include it, except just now.
Is it like mandatory though?
So this gets into personal choice. So I honestly don't know. Because when I tried to look, do you have an answer?
Yeah, it reads the next statement, so if the next statement is a begin, it will read everything as a begin to end, but if
Okay.
it's just up to a semicolon, you can put a single line.
Okay, so it's kind of the same as C and Java and other languages. It's basically doing one statement after this, but if it's a begin, that begin end block is considered one statement. But I really, really strongly recommend, especially when you're learning, not to try to take advantage of that, right? And even in my last quarter programming course, I'm still telling students this, and I still see students get caught up by this. If you work with the assumption that, if I just put one statement here, everything's going to be fine, and you decide to add another statement in here, right, and you don't remember that you have to now put a begin end, you can end up chasing that bug for a good hour or two sometimes. So for me, I don't want to have to think too much, right? So I always put a begin end around if statements. I always put a begin end around always blocks. I always put curly braces in Java or C when I'm writing an if statement, even if I've only got one statement in there. It's just personal choice. And the other thing you hear me say a lot is, right, there's a whole lot to Verilog, and we're doing a really tiny little slice of it. So, but you can go online, you can find, multi-volume books on the language, and it does a whole lot more than we're touching on. All right, so if T is 1, we want X to toggle, otherwise we don't want X to change. Yeah?
So what if you do an exclamation point instead of the tilde?
I think exclamation marks work also for negation.
They work. Is it different?
I think it's just dealer's choice,
Okay, cool.
but let's find out. Let's just try that. Yep, that looks fine to me. It's kind of one of these things where different languages use different things, and sometimes it's easier just to give people a choice than to, like, say you must use a tilde. So there's options. So when we compile this program, this code, we're describing a circuit. So what circuit are we describing? We know it's acting like a T flip-flop, but this doesn't say, make a T flip-flop. This says do something very specific. So here's what this might synthesize to. Positive edge clock means we probably want a flip-flop somewhere, so we're going to have a flip-flop, and I'm just going to say this is going to be a D flip-flop. And so it's got a positive edge triggered clock, and this is certainly going to be connected to clock. And so what's going to happen on the positive edge, whatever value is in D is going to get set to Q. Okay, so this is going to be connected to X, right? Or named X. And it says if T is equal to 1, set X equal to the complement of X. If T is equal to 0, then we don't want to change the value of X. But this is still going to tick when the clock ticks, right? This is still going to take the value of D and load that into the flip-flop. So here's what we can do. We can take this and we can have a 2-to-1 mux. So this can be input 0. We can take this, complement it, put that into input 1. And then T can go into your select input. Here's your output. And this is a 2-to-1 mux. Okay, what does all that mean? If T is equal to 0, this mux says take input 0, send that to the output. So if t is 0, the current value of x comes around, loads into D, that gets loaded into the flip-flop, the output is still x. But if t is 1, then the select value is 1 on this 2 to 1 mux, which means that x invert is coming into input 1, that's what's coming out of the output. So if t is 1, you have x bar sitting right here, and when the clock ticks, x bar gets loaded into the flip-flop, and now your output is toggled. All right, this was an old homework question from the previous homework set, implementing a T flip-flop with a D. So this is something like what would be built from this chunk of Verilog. And it may look kind of like random or goofy, but it's a model for how a lot of these always blocks can actually get coded. And when you write a synthesizer, right, to take Verilog and turn it into hardware, you tell it basically how to do things like this. And it's not as bizarre as it might seem at first. Let me show you what you don't want to do. So this is a bad T flip-flop. So here's a D. Here's our clock. Here's Q. We're going to call that X. We're going to take this. We're going to invert it. We're going to feed that back into D. Here's our clock. Here's T. We're going to AND those together. So if t is equal to 0, what happens when the clock ticks over here? Absolutely nothing. Because if t is 0, you got a 0 going into your clock. Doesn't matter if this clock over here is toggling between 0 and 1, the output of the AND gate is still a 0. Nothing changes the flip-flop, your output is unchanged. If t is 1, then the clock passes through this AND gate, and now each time the clock ticks, the current value of x gets complemented and loaded in to the flip-flop. So in theory, this looks like a really good way to design a T flip-flop, but it's considered really, really poor design. The problem with this is you have one clock running in the system. Okay, one master clock that's supposed to go everywhere that needs to be clocked. And you try to set it up so that that clock hits all of the things that are being clocked roughly at the same time. Right? There may be little wire length differences, but more or less you want all your flip-flops to respond at the same moment. Except this poor flip-flop over here doesn't respond until this clock passes through this piece of logic. And there's a propagation delay associated with gates. So this flip-flop's going to be flipping at a different time from the other flip-flops. And that's a problem, because that's where we get glitches from. And we know glitches lead to all kinds of bad things. So the golden rule is don't gate your clocks. Right? All the clocks should go directly into the clock inputs of your flip-flops. And if you want to do something like, you know, maybe choose to ignore the behavior of the flip-flop, right, you got to do something with circuitry. And the propagation delays here don't cause me any harm, right? Because that's happening in between the clock ticks. But we want all of our devices to update synchronously. Okay, synchronous design is the name of the game. So if you try to write a circuit like this in a better design tool, it'll actually warn you that you have gates on your clock line. And it gets really unhappy. Clocking is a whole nother area. You can do a whole PhD just on clocking. All right? It's a huge area because the timing is so critical and so many things need to be clocked, right? Everything inside your system has to be clocked. There was an old processor called the Alpha. It was a microchip version of the VAX processor, and it had what was called the foot-long hot dog. Now it was a microchip, so you know the chip was about that big, but supposedly if you took the clock line and unfolded it, it would be about a foot long, right? But it was serpentine in these, like, you know, Greco-Roman patterns where it farms out into all of these little fractal type areas. and so on, to try to get it from your input to the chip to all the different elements in roughly the same path length, to try to minimize what we call clock skew. So design of good clocking systems and so on, that's like another one of these amazing areas of computer architecture that you can spend a career on. All right, so we don't want to gate our clocks. What else should we play with? I'm not ready for state machines yet. Let's look at the counter. All right, so we're going to design a, looks like a 3-bit counter. I've got my clock that's ticking every 10 nanoseconds as before. I initialize my clock to 0 just to give it a defined value to begin with. At 10 nanoseconds I'm going to hit my reset line, and then at 30 nanoseconds I'm going to clear my reset line. So reset is used to zero out the counter. And go is used to say go ahead and count every time the clock ticks. So I'm going to set go to 1, I'm going to wait 600 nanoseconds, I'm going to set go to 0, I'm going to wait 600 and set it to 1, and so on. So the actual counter looks like this. So at the positive edge of the clock we do the following. If the reset line is 1, meaning 0 at the count, I set my output to 0. Otherwise, if reset is not 1, it's 0, check to see if go is equal to 1. And if it is, set output equal to output. I'm going to actually do output plus 1. Alright, so we'll increment the output. And that's my whole always block. That's technically one line of Verilog. So first check to see if reset is asserted, and if it is, clear the count. If it's not, now check to see if go is asserted, and if it is, increment the count. And if it's not, we don't do anything. Remember, this is synthesizing hardware, so it's really easy to accidentally write something that tries to give output 2 different values, right? And you need to make sure you're not asking it to do that. So here I'm very clearly saying either output is going to be set equal to 0, or it's going to be set equal to output plus 1. It's not going to try to do both. Okay, if I didn't have an else, I would get a compile error. And by the way, I have a script called go that lets me just say go counter, and it'll do all these things that I keep typing. iverilog-o, counter.v, and then vvp, and so on and so forth. So if you're in an environment where you can do scripting, you can save yourself some time like that. But we'll just do it by hand so we get to see the commands a few times. So we'll compile counter.v, we'll put the output in counter.o. We'll simulate counter.o, or .out. And it created a counter.vcd. So let's look at that. And so there's our clock up at the beginning. Well, let's put our reset at the beginning, and our go, and our clock, and our output. And zoom out. And we got a really fast clock going up and down really fast. And reset line started off high and then went low. That's out of the action after that. Let's expand our output. And you can kind of see what's going on. So the least significant bit is at the bottom, and that's wiggling really fast right along here. The next bit's wiggling at half the speed. The most significant bit's wiggling at half the speed. Right, so this is column 3, which is, you know, a bunch of zeros and then a bunch of ones every 4 times that this one changes. So we can zoom in and see a little better what's happening, right? Every time that, so the go line goes high here. On the next rising edge of the clock, our output is 001. And if you make this wide enough, you can see the output value here. It says 001. If we go to the next rising edge, the output becomes 010. You can see that value over there, and you can look at the actual signal 0, 1, 0. So it counted to 1, 2, 3, 4, 5, 6, and if we scroll over, there's 7, and then it goes back to 0. So that's a 3-bit counter. And that continues for 600 nanoseconds until our go line drops. So our count got up to 6, and then at this point our go line dropped, and on the next rising edge of the clock nothing happened. And from this point forward the count just remained stable. It's just constantly 6. So if you want a down counter, set out equal to out minus 1. So just change that. Whoa, I did something weird. There we go. Right, so change that minus to a plus, it's an up counter. Make it a minus, it's a down counter. Alright, so now it's counting from 0 down to 7, 6, 5, 4, 3, 2, 1, back to 0, and then back to 7. So if you want an up-down counter, which can do either, well, sometimes we want to say out is out plus 1, sometimes we want to say out is out minus 1. Put in another if statement. So if go equals 1 begin, have another input, I don't know, call it up. If up is equal to 1, out is assigned out plus 1, else out is assigned out minus 1. You got an up-down counter now. One extra if statement. So there's examples, right, in that quick start guide. And it's worth, you know, putting some of these things in, making sure that they work, and then modify them. Right? Start making changes to them and imagine different things they might do and see what you can get them to do. And it's just another language, right? It's weird because, like I say, it's not an algorithm, but it's still just another language that just takes practice to get more fluent in. So questions up to here? And when I ask that, it doesn't mean I expect you to understand everything that we've been doing so far perfectly. It takes time to gel. Like I say, for me it took like 3 years. But you can still have questions though. Sometimes they're just hard to articulate. Yeah?
For experiment 5 for the 5 out of 16 event detector.
Mm-hmm.
When so let's say you have a counter that counts from 0 to, I think 0 to 16.
Okay.
So do you want us to like reset the counter when it hits 16 or when it's greater than?
No, so that's one way to try to do it, but it's not going to get you there because the problem is not saying look at 16 inputs and now tell me if 5 of them are 1. Now look at the next 16 inputs and tell me if 5 of them are 1. You really want a moving window. So each time you get another input, you want to look at the last 16. Right? So counting the number of ones is not going to do exactly what you need. Because, you know, if you get a 1 here, let's say you get 5 ones. I'm going to go right to left instead of 0. So at this point we'd have 5 ones. And I'm going to guess that that's 16. It might be off by 1. Right, so now 16 events, we had 5 ones. Our output should still be a 1. The next time that we get an input, right, that one falls off the window, and now our output should be a 0. Right? But if this input had been a 1, now we would say, okay, last 16 events, we've still got 5 ones, so our output would still be a 1. But question 4, experiment 4, is building a shift register.
Okay.
And that's actually what you need for experiment 5. Because what we need to do is we need to look at the last 16 values that we saw, and we need to do that in a way so that the next event that we get, we forget about that first event that we saw and we just remember the last 16. That's really what a shift register will do for you. So if you take your events and you shift them into a 16-bit shift register, now all you got to do is count how many ones you have in that shift register, and if it's equal to 5, set your output to 1. Otherwise, set your output to 0. So it's a combination of the shift register from experiment 4, but 16 bits instead of 8, and then some combinational logic that basically counts the number of ones.
Right.
And there's different ways to count ones. The easiest way to do it, though, is just add up all of these bits and see if the sum's equal to 5. Because we can add bits, we can just say plus, right? And it's a really big assignment statement, but that's okay. And it's really cool once it works, because if you look at the timing diagrams, if you look at all of these internal values in the timing diagrams, you can really clearly see how they're shifting across time and how your output's responding. Do you have a question? Okay. So let's talk about this thing. So I've said inside always blocks, you should always use this symbol. Okay, this is called a non-blocking assignment. Non-blocking means it happens more or less instantaneously, and it doesn't stop other things in your Verilog program from happening. In other words, it lets things happen in parallel. And hardware is parallel, right? Computers, for all the great things that computers do, they're fundamentally sequential. They do one thing at a time. They do it in like 1/3 of a nanosecond, right? And they can do it for months, but they're still doing one thing at a time. If you've got 4 cores, okay, they do 4 things at a time. But your set of instructions are basically sequential, okay? The universe is not sequential. The universe is parallel, right? Every piece of state information about every particle at every point in the universe is being updated at the same time as every other one, right? The universe is parallel. Hardware is parallel. So hardware is in some ways a much better map to the universe than a computer. This is why computers are not so good at simulation. Basic things like 3 bodies orbiting around each other, what's the position of these things a year from now, you can't really do that on a computer. You can approximate it, but it's a chaotic system. And your small errors just build and build. There's a really good book called 3-Body Problem. It's part of a trilogy if you want to read some cool sci-fi that kind of deals with that. The universe has no problem solving the 3-body problem. Just take 3 bodies, put them in orbit around each other, there's your solution. So hardware is inherently parallel, and we like to build hardware circuits to take advantage of that parallelism. And if you use these non-blocking assignments, you maintain that parallel behavior of your circuitry. Now, if you use an equals sign, that will work, okay, inside an always block. It will copy the thing on the right to the thing on the left, but this is a blocking assignment. And we don't usually want a blocking assignment because we're forcing our parallel hardware to act like it's sequential. And anything that comes after this will not happen until this assignment has taken place. So it's acting more like code. Right, so don't do that. So let me show you the effect of this on synthesis. We can do negative edge also, by the way. I just always do positive for some reason. So always the positive edge clock begin. And suppose we've got a register set up and things like that. Let's do the following statements. B gets assigned to A, C gets assigned to B, D gets assigned to C. And suppose yeah, we'll just start off with that. Suppose A is 1, B is 0, C is 0, D is 1. Okay, so what's going to happen to the values of A, B, and C after this block of code executes? That's a misuse of the term because it's not a program, but you know what I mean. After the clock edge ticks, B is going to get assigned to A, right? So B is going to be equal to 1. And, sorry, B is going to get copied to A, so B is a 0, so A is going to be a 0. And C is going to get copied to B, so B is a 0, C is a 0, so B is still going to be a 0. And D is going to get copied to C, while D is a 1, so C is going to be equal to a 1. And this is a shift register, right? We're taking these values and we're just moving them down one spot. Okay, suppose I write this differently. Suppose I change the order. C comes from D, B comes from C, A comes from B. And we're back to our original initial values. So C is certainly going to take on the value of D. C is going to be equal to 1. What value is B going to get? It's a trick question.
Maybe like C next, essentially, or the current value that you got for C.
There in some instances is going to be an initial value of C.
Yeah. So remember, this all happens in parallel. So at the same time that C is being given a 1, B is given the value that C currently has. Well, C is equal to a 0, so B is going to be assigned that value of 0.
So it's always going to be the initial value?
It's always the initial value, right? And at the same moment, A is assigned whatever the initial value of B was, which is a 0. And so we get exactly the same result. The order doesn't matter because they're really parallel. And one way to think of this is when the clock ticks, what's the value of D? It's 1, okay, C is going to be equal to 1. When the clock ticks, what's the value of C? It's a 0, okay, B is going to be a 0. When the clock ticks, what's the value of B? It's a 0, A is going to be a 0. Every statement in there basically happens at the same moment when the clock ticks. Okay, but that's only because we're using these non-blocking assignments. Now, if we did this, C equals D, B equals C, A equals B, that says when the clock ticks, take the value of D, copy that into C. Okay, C is equal to 1. And then after that happens, take the value of C and copy that into B. Okay, so C is equal to 1, B will be 1. And after that happens, take the value of B, copy that to A equals 1. Totally different behavior. And the compiler won't mention anything to you about this, right? But this is definitely doing something different from this. So best advice, never put equals inside an assignment, inside an always block, right? Always do this non-blocking assignment. Yeah?
Can you use that to like your advantage so you could like preload maybe
Yes.
reset?
Yeah, so you can use this to your advantage if you understand that it's making it sequential. And that's why it's available as an option. But other than that, if you just want to do things right, try to do them in parallel. And the synthesis turns out to be very different, right? This will actually synthesize as one flip-flop, and whatever value C has will also be routed by a wire to B and A. This will actually synthesize as 3 flip-flops. Okay, so keep working on the homework in the lab, and we can talk about questions on Thursday. And Thursday, I want to look at how we do state machines with all of this stuff, and that'll be moving us towards the end of Verilog. All right, so I'll see you Thursday.